Consider the following scenario. Car B races along a circular racetrack and is constantly 2.5 feet from the center of the racetrack. It starts at the 3 o'clock position and travels at a constant speed. The angle subtending its path sweeps out 2 radians per second. So we'll let t represent the number of seconds since the race car started moving, and we'll let g of t represent the race car's distance to the right of the center of the racetrack in feet in terms of the number of seconds t since the race started. So let's draw a diagram of this. So we have our circular racetrack. Let me draw that a little larger. We've got our circular racetrack. Car B starts over here at the 3 o'clock position and then begins traveling counterclockwise. And it does that at a constant speed. Then we have an angle that subtends the race car's path. And so as the race car races around that circular ski trail, that angle opens up in the counterclockwise direction. And we'll just say theta represents the radian angle measure of that angle. So since the race car travels at a constant speed and the angle sweeps out 2 radians per second, what this means is each second that passes, that angle sweeps out 2 radians. Or a better statement would be, for any number of seconds that elapse, the angle sweeps out 2 times as many radians. So like if 1 second has elapsed, the angle sweeps out 2 radians. If 1.5 seconds have elapsed, the angle sweeps out 2 times as much as 1.5, so 3 radians. And in general, the angle will sweep out 2 times as many radians as there are seconds that have elapsed. And therefore, theta, the measure of that angle, will be equal to 2 times t, 2 times as large as the number of seconds. Therefore, anywhere we think about theta, we can actually think of that as 2 times t. They both represent the radian measure of that angle. So if we wanted to look at this car's distance to the right of the center of that racetrack, right there, then we know that distance is cosine of theta radii, or radius lengths. And since the radius of that racetrack, well, it's really the car's path around the racetrack, the car is constantly 2.5 feet from the center of the racetrack, and therefore, the car's distance to the right of the center of that racetrack is 2.5 times cosine of theta feet. However, we just decided that theta and 2t both represent the radian measure of that angle. Therefore, anywhere we see a theta, we can actually replace it with a 2t without changing the meaning. So here we could change this with a 2t, and here we could replace that theta with a 2t. Now in this case, 2.5 times cosine of 2t gives us the race car's distance to the right of the center of the racetrack in feet in terms of the number of seconds t. But we decided that's what this function output g of t was going to represent, and therefore g of t is going to be equal to this expression over here. We could say g of t is equal to 2.5 times cosine of 2t. And therefore, we have a function definition for this function g. It's worth pointing out that this angle must sweep out 2 pi radians for that car to make 1 full lap around the circle. So if it was traveling at 1 radian per second, then it would take 2 pi seconds to make a full lap. However, this race car is traveling at 2 radians per second, or twice as fast, and therefore it should take half as long to make 1 full lap around that racetrack. And therefore, it should take half of 2 pi seconds, or 2 pi divided by 2, which is just equal to pi, seconds to make 1 full lap around the racetrack. And therefore, it takes pi seconds, so pi seconds, for this race car to make 1 full lap around the circular ski trail. Since it's traveling twice as fast as 1 radian per second, which is kind of like just thinking about theta being equal to t, things basically just happen twice as fast. It takes half as long to make 1 full lap around the track, and therefore if we looked at the function graph of g, we should notice the output values making a full cycle of values twice as fast as the normal cosine function would.